Hi everyone, welcome to our presentation on reproducing and extending the practical GAN-based synthetic IP header trace generation using NetShare, which was recently published and presented in SIGCOMM 22. I'm Shyaman. My colleague Divyanshu and I worked on this project. In this presentation, we will first discuss the NetShare model and how we reproduce its results. Then we will move on to our extension of this method. So let's get started. First of all, let's start with some use cases of network traces. Network traces are used in a variety of ways, such as predictive modeling, like anomaly detection and fingerprinting. They also enable data-driven network monitoring algorithms and testing. Also, benchmarking of new hardware and software. Therefore, there is need of good quality data to accomplish these tasks. However, collecting and sharing IP header traces can be challenging due to privacy concerns and legal restrictions. It can also be a time-consuming and costly process. This is where synthetic IP header traces comes into play. By generating traces that mimic the statistical properties of real traces, researchers can explore network behavior and test hypotheses without compromising individual privacy. In this presentation, we will explore how generative models can be used to generate synthetic IP header traces. Tabular generative adversarial networks or tabular GANs is a very popular approach to generate synthetic data using generative models. Here GANs treat packets or flow header traces as tabular data. However, when it comes to generating IP header traces, the tabular GANs have several limitations. Basically, they can't generate high fidelity traces and also they don't perform well on downstream applications. So one of the main issue is tabular GANs cannot capture the temporal dependencies and correlations present in the IP header traces. To address these issues, the authors formulate this problem as a time series generation problem. Here they have got series of data, let's say data is spanning from day 1 to day n, and they merge these data into a large single trace. Then they perform flow-based split based on the 5 tuples. Further, they splitted these flows into time duration chunks. Here, instead of the tabular GAN, they feed the data into a time series GAN. So each of the sample is a series of packets that contains information such as packet size and timestamps. This allows the model to capture long-term temporal relations much more effectively than the tabular GAN, where each sample is a single packet. However, if you attempt to input the large traces into the model, there is a possibility that it won't fit to the memory of the RAM or GPU. To tackle this scalability issue, they made some adjustment to the training process. Instead of feeding the entire flow traces as a single chunk, they partition the large traces into smaller chunks. The first chunk was used for the warm-up training, and the subsequent chunks were trained based on the initial chunk in parallel. This approach provides two significant speedups. First, the following chunks were not trained from the scratch, but from the baseline model. Second, the chunks were trained in parallel instead of training them sequentially. So this approach can reduce the total training time significantly. So let's look into the evaluation of this method NetShare. For the evaluation purpose, the paper used two popular datasets, UGR16 and KIDA dataset, which are widely used by the network researchers. Here we also use the same two datasets for the evaluation of the model. The authors have shared the source code and it served as the basis for re-implementation. But we discovered that the original code has bugs and it was optimized for training models on resource-intensive CPU clusters. Also, their recent release of PyTorch implementation, much of the code was still not functioning properly. To address these issues and make the code scalable and efficient on GPUs, we made several modifications. Although we were successful in running NetShare on the UGR dataset, we encountered issues with the KIDA dataset running. Therefore, to evaluate the model, we used the synthetic data generated for KIDA dataset in the original web. We have shared our modified code on the GitHub for others' use. Here we evaluate the fidelity of generated traces by comparing the statistical distribution of various features between the real and synthetic traces. The figures here show the cumulative distribution of flow sizes in the KIDA and UGR16 dataset, along with the distribution in the generated traces from NetShare. So as you can see, the distribution of generated traces closely match with the distribution in the real dataset, indicating that the NetShare model is able to accurately capture the statistical distribution of flow size in the real dataset. Next, we looked into the distribution of flow volume in UGR16 dataset. As you can see from the plot, the generated traces by NetShare closely match the real UGR16 dataset in terms of flow volume. This also demonstrates the ability of NetShare to generate realistic traffic traces with high fidelity. Finally, we looked into the top 5 service destination port and IP protocol frequency in the UGR16 dataset and the generated traces. Here we can see that these two distributions are also very similar to that of the original dataset. The fidelity of the NetShare generated traces was supported by the fact that its distribution is closely matched those of the original dataset in terms of flow size, flow volume, and different packet properties. Next, my colleague Divyanshu will discuss and demonstrate the extension of this work, including the use of diffusion models to generate synthetic packet traces. Thank you.
I will be presenting how we have used the diffusion models to generate the synthetic flows. So this model is built on top of the original model, NetFlow, developed by the authors. So firstly, why even use the diffusion model? So for that, let's look at some images. These images, all of these very interesting looking images were generated by the stable diffusion model, which came out last year. And for all these image generation, we basically just had to input a text prompt and it would generate an image based on what you asked. And similar models have been developed for video generation, music generation, speech generation, any generative task you can name, uh, like even for satellite data generation. So the whole generative machine learning field has been taken away by the diffusion models. So what pros the diffusion models have over GANs? Uh, so the GANs are very good one-shot generative models and they are very fast, but they are harder to control while generation. And also the min-max training objective that they use is prone to collapsing. And further, the diversity in the GANs is not to the expected level. Moreover, coming to the diffusion model, we have pretty slow generative speed because they utilize something called multi-iteration approach, which we will shortly see what it is. But they are in turn easier to control during generation, and the objective during training is pretty simple and easier to train. And more importantly, they provide a vastly diverse generations than the GANs, which is the desired property in the synthetic data generation for any task. So let's give a quick introduction to what diffusion models are. So given any input, let's consider this cat as an input. There is a forward diffusion process in that we iteratively add noise to this data until all we are left is the noise. And side by side, there is a generative reverse denoising process, which tries to learn to denoise this image of cat. So in here, there is a neural network which is learning to denoise this image of cat at each timestamp, and the forward and the reverse timestamps are both the same amount. So we can more clearly see it in this below image, in which the p theta is our denoising model, which is used in the reverse denoising process, and Q is our forward diffusion process, which is adding noise. So P theta is trying to denoise it, and Q is iteratively adding noise in the forward step. And so now, why can't we just directly use the diffusion models for our task? First and foremost, they are very computationally expensive, and they require a lot of timestamp, that is like a lot of iterations of noising and denoising for training and also for the generation. And this is mainly because the forward process is often approximated as cosine, and this approximation only holds when the number of timestamps is high, or the beta t, that is the amount of noise that we are adding, is very less. So that's why we need a lot of timestamps. And also, diffusion process assumes that the whole data is falls under a singular Gaussian distribution, which might not be the case in for our data, which is the flow data, because it has multiple attributes and features, and they all hold different. They all might hold a different distribution, so they can't be just directly assumed to be having a singular Gaussian distribution. So now we need some different technique with respect to diffusion model if we want to use them for our task. So we already know that the generative adversarial networks, the GANs, are very good for generating flow data as demonstrated by the original authors. They are able to generate high quality samples and also very fast, but the samples are not very diverse. Diffusion models, on the other hand, generate high quality samples, but the diversity is also really good, but the sampling rate is very slow. So if we were able to somehow merge the GANs and the diffusion models, we could develop an ideal model for our task. But how do we do that? So for this, we develop a conditional GAN-based TTPM. And this idea is derived from the two works. Firstly, the ILVR, conditional method for denoising diffusion probabilistic models, which was a spotlight paper at ICCV, and they're tackling generative learning trilemma with denoising diffusion GANs, which was also one of the top papers at ICLR 2022. So, as you can see, our training regime utilizes both the diffusion process, and also we utilize the adversarial training that GANs use using the discriminator and the generator. So let me just quickly give you the technical description of this whole training regime. So in the forward diffusion, it is pretty similar to the existing diffusion model, but with one assumption that the number of diffusion steps should be small, and each diffusion model, each diffusion step, that is the beta t, can be very large. And now coming to the core of the training process involves matching the conditional GAN generator with the true denoising distribution using an adversarial loss that minimizes a divergence per denoising sample and per denoising step, sorry. Uh, and the adversarial training setup, which consists of time-dependent discriminator. As you can see, the discriminator takes xt minus 1, xt. These are both the steps in the forward diffusion, and t, which is a time vector. So the adversarial training setup consists of a time-dependent discriminator, which takes input vectors and decides whether the denoised version of the input is plausible. The discriminator is trained by contrasting fake samples from the generator against real samples from the true denoising distribution. And the conditional GAN approach addresses the limitation of existing diffusion model by modeling a more expressive multimodal denoising distribution. That is our hypothesis, and we hope that it would work for our flow generation task. Since it has already been able to work very good in case of image generation, as demonstrated by these two papers that we have mentioned, uh, we felt that it should be a good approach to use for our task. So we basically, instead of like the image here, you can just think of it as a flow, and we are adding noise to the flow in the forward diffusion process, and the whole of the description remains the same as I described earlier. So we take the original NetFlow model, we just replace the time series GAN training regime with our diffusion-based technique, and we keep rest of the training regime completely same. So now let's look at some results, whether our model was actually effective or not. So we will compare our model with the results from the NetFlow model. So firstly, let's compare the single feature distribution similarity score. So for the feature TS, as you can see, our model score is way better than the one provided by the NetFlow. And as you can see, our plot of like the data distribution conforms very well to the real data distribution, while as you can see that for the NetFlow model, it is not the case. And here the score lower, the better. And now coming to the byte, as you can see here too, our scores are better than the NetFlow model. The NetFlow model is at the right, NetFlow model is at the left, and our model is at the right. And as you can see, for the type, all type are like the scores are nearly similar. But for the packet, as you will see, we have gotten a better uh, data distribution than the NetFlow model. And also for the TD feature, we have got a better score than the NetFlow model. So you can see that our diffusion model training regime worked pretty good for the single feature distribution similarity, but there is one caveat. Our model performed bad compared to the NetFlow on the attributional data generation, which is primarily because that the attribute data generation mostly utilizes categorical data, and during our diffusion process, while we are sampling the basically when we're adding noise to the data and to the generated noisy samples, we aren't reducing them to categorical data. They are rather continuous data. So we expected this kind of performance drop since our data is continuous, but it requires a discrete data to be more precise. So as you can see, our source IP scores are way bad than the original NetFlow. Our destination IP is around similar to the NetFlow. And you can, for the full list of results for the attributional distribution data, basically there are 5 of these fields. You can see the PDF that we have attached along with the report. And you will see, notice that the attributional distributional similarity is low compared to the NetFlow. And this was actually expected since we are not reducing the noisy samples categories to the discrete domain. They are rather in the continuous domain. So we expected that our diffusion-based model might not be able to learn the underlying data distribution properly. So I would say our experiment was a success because we were able to get a good uh, model which could provide a good feature-based distribution scores, but our attribute similarity scores were low. But if we given more time, we would have been able to devise a proper training regime for the attributional data too. So I think it is pretty doable, and we can focus it on in a future research work. Thank you.